Do 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 do. So let's look at how we can apply Newton's first and second law to examples where we have an applied force that is not strictly horizontal or not strictly vertical, but instead at an angle. So we're going to work through two examples here and see how they work out. So let's take a look at example number 1. So it says here, my kid is sitting on his wagon on the ground. In order to pull him, I need to continuously exert a force of 24 newtons at 35 degrees above the horizontal. How much does Ezra, that's my kid, weigh if the wagon is 2.0 kilograms and mu equals 0.10 between the wagon and the ground? So we've got a lot of information here. First thing we always want to do is draw a diagram. So my kid on his wagon looks like a rectangle. Perfect. And that rectangle is on the ground. Let's make this drawing a little bit better. Let's actually make it sitting on the ground. Beauty. Okay, so first thing we do, we draw our diagram, label all our forces. So I'm pulling at a 35-degree angle above the horizontal. So we're pulling like this. Here's that applied force of 24.0 newtons. And it's 35 degrees above the horizontal. So if this is parallel to this angle in here is 35 degrees. If we take this force, we can actually break it up into its components, Fx, and here, Fy. It's going to be helpful for us. Okay, what else do we have here? Well, we've got the force of gravity pulling down here. So we've got Fg. We've got the normal force exerted upwards, N. And we have, it tells us there's a coefficient of friction, so we've got friction opposing the motion. So we've got friction here. Okay. I think we've labeled all our forces. Now we need to decide, are we using Newton's first or are we using Newton's second? So it says here, in order to pull him, so it doesn't say anything about pulling him faster or slower or anything, so we can assume that it is a constant motion. So what does this tell me? We're looking at Newton's first law, which means that the net forces are equal to 0. So everything in the x direction has to cancel out, everything in the y direction needs to cancel out. So that's what we're dealing with here. Okay, so ultimately we want to know Ezra's mass. So where are we going to get that mass from? Generally from the force of gravity is what we're going to be looking for here. So how do we find the force of gravity? So we want to know Fg equals m times g. So we can rearrange that to give us the mass equals Fg divided by g. We know gravity, or the acceleration due to gravity, is 9.81 meters per second squared. Do we know the force of gravity? No, not currently. What do we know though? It's not accelerating up or down, so we know that all of the forces pointed up and all of the forces pointed down have to equal out. So what do we have pointed down is Fg. That's the only one we have pointed down. And we know that it has to equal the ones that are pointed up, which are the normal force and Fy. So we have N plus Fy. Do we know either of these right now? We don't know N. Do we know F of Y? No, but we can solve for it. So let's say for F of Y, it's just the component in the y direction of our applied force. So if this is our angle we're talking about, over here is the opposite. Here is the hypotenuse across from the 90 degree here. So opposite and hypotenuse is sine, right? Opposite, so kato, so sine. Yeah, so sine theta equals opposite over hypotenuse. And if we fill this in, we have sine of 35 equals the opposite side, which was Fy, divided by the hypotenuse, which was 24. Rearranging for Fy, we get 24 times the sine of 35. And when we get that, we get 13.8 newtons. So now we know that F of y. So we can substitute this. I'm just going to circle it. And we're going to substitute that into here. Do we know the normal force? No, not yet. How can we solve for normal force? So you can see we got to do one thing to get something else, and so on and so forth. So what's another formula we know with normal force? Well, we know the fun formula. F equals mu times n. If we rearrange for n, that tells us we have friction divided by mu. Do we know what friction is? No. Oh no. How do we solve for friction? Well, we know that the forces are balanced in the x direction, so we know that this force of friction has to be equal to F of x. So we can actually say here that this is equal to F of x divided by mu. And F of x, similar to up here, except instead of using opposite and hypotenuse to give us sine, we're going to use adjacent and hypotenuse and cosine. When we rearrange so that we get to this point, F of x is going to be 24 times the cosine of 35. And mu was given in our question is 0.10. So when I solve for this, I get 197 newtons. So my normal force is 197 newtons. So that's good. We needed that because that is going to get substituted into here. So force of gravity, which we need to go back to get our mass, is the normal force plus the Fy. So we just got those 197 plus 13.8 gives us 210 newtons. I've just rounded here. So 210 newtons. Why do we need Fg? Well, again, we're going to take that and substitute it into here. So we have 210 newtons divided by 9.81 meters per second squared gives me 21.4 kilograms is the mass. Is that the end of the question? So close. I threw you a little extra in this question. How much does Ezra weigh if the wagon itself is 2 kilograms? So the mass of Ezra is just 2 kilograms less than this. So mass of Ezra equals 21.4 minus 2.0 gives me 19.4 kilograms. And I believe we should be to 2 significant digits, so 19 kilograms. Hopefully in your notes you've made this a little bit more laid out than I did, a little bit more neat than me. But so long as you can follow, hey, in order to do this, we had to do this. In order to do this, we had to do these different calculations down below. So you really have to think about this sequentially. If I need to use a number and I don't have it, how do I solve for it? And we may have to keep doing multiple steps. All right, let's look at example 2. So example 1 was using Newton's first law where all the forces were balanced. Example number 2, a man walks up to a skateboard which has a mass of 3.5 kilograms and pushes with a 115 Newton force down at an angle of 60 degrees from horizontal. If mu equals 0.20, what is the initial acceleration of the skateboard? Here's a clue. Acceleration. If we're talking about acceleration, we don't have balanced forces, so we're looking at Newton's second law here. So I'm going to even write that up here. Newton's second law. So I know I've gone out of order. I should have drawn my diagram first, but I noticed that, so let's go with that. So here's our skateboard. Looks pretty similar to my kid on his wagon. It is a rectangle on the ground. Okay, what do we have? We have the force of gravity here acting downwards. We have a normal force acting upwards. Let's make that a little bit bigger. I'm not drawing these forces to scale, so don't get confused by that. I'm going to just draw it a little bit bigger so we can see it more clearly. So we've got those two. We also have someone pushing with 115 Newton force down on it. So we're going down on here with a applied force of 115 newtons. We also have coefficient of friction. So we have friction that's going to be pointed this direction. So F, ooh, that's a terrible looking F. Let's try that again. F, there we go. And do we have any other forces? I don't think so. What I like to do is I like to take that applied force and break it down into its components. So we have Fy and Fx here. And here is my angle of 60 degrees. Okay. So we want to know what is the initial acceleration, and we said this was Newton's second law, so we know the net force is equal to mass times acceleration. Rearrange for acceleration, that means our net force divided by mass. And it's going to accelerate in the horizontal. It's not going to be pushed down through the ground. It's not going to float. So I'm going to even clarify this a little bit further and say the net force in the x direction divided by the mass. Okay, do we know any of this stuff right now? Yeah, actually we know the mass. I should have labeled it on here. I like writing it in here. Mass equals 3.5 kilograms. So we know 3.5 kilograms. Do we know our net force in the x direction? No, we don't. However, we can find it. So here we go. We're going to have to start drilling down, solving one thing to solve for another. So we know that the net forces in the x direction are going to be this, subtract this. It's actually going to be moving this way. Again, I didn't draw these to scale, so this is actually, we're going to find is bigger than this. But it's, so we're going to have fx minus f. Okay, can we find either of these right away? Yeah, we can find f of x. If we label our triangle here, here's my angle, this is opposite, this is adjacent, here's hypotenuse. So we're using adjacent and hypotenuse, which is cosine. When we rearrange, so we'd say cos theta equals adjacent over hypotenuse. When you rearrange for the adjacent, which is f of x, we get that it is going to be 115, which is the hypotenuse, times the cosine of our angle, which is 60. So 115, I need to pull out my calculator here, 115 times cosine of 60 is 57.5 newtons. So we can use that right here. So we've got one part of this, so 57.5 newtons minus our force of friction. Do we know our force of friction? No, we don't. So guess what? We got to solve for it. So we use the fun formula, F equals mu times N. We know mu, it's given to us in the question. It is 0.20. Do we know the normal force? So let's fill this in, 0.20 times the normal force. Do we know it? No. Again, we got to keep working away at it. So what do we know? It's not going down through the ground. It's not floating, so all the ups have to equal all the downs. So the normal force is the only one pointed up, and it has to equal this plus this, the two that are pointed down. So the normal force equals Fy plus Fg. So Fy, instead of cosine of theta, we would be using sine of theta is opposite over hypotenuse. Fy is the opposite, so when we rearrange, we're going to really be doing 115, the hypotenuse, times sine of 60. How do we find Fg? Well, Fg is just the mass times gravity, right? So we have 115 sine 60 plus the mass was 3.5 times the acceleration due to gravity, 9.81. Let's see what we get when we do this. 115 times sine of 60 plus 3.5 times 9.81 gives me 133, actually 134. 134 newtons. All right, why were we solving for the normal force again? Oh yeah, right, so we could plug it into this part right here. So we plug in 134 newtons. So if you still have that in your calculator, just put times 0.2, gives me 26.8 newtons. That's our force of friction. Why did I want the force of friction? Oh yeah, I wanted to put it in up here. So we have 26.8 newtons. So 57.5 subtract 26.8 gives me 30.7 newtons. That is the sum of my forces in the x direction. Why did I want that? Oh yeah, so I could put it in the acceleration. So we keep working our way back here. So 30.7 newtons divided by 3.5 kilograms gives me 8.8 meters per second squared. And that is our final answer. Whew! A lot of steps. We got to work backwards. You keep looking, and I stress this over and over again. You start with your diagram, determine whether you're using newtons first or second, and then start working your way through the calculations from there.